Welcome to Electrical Engineering with Excel. This video is about the development of a spreadsheet that does the calculations of resistor values for comparators with hysteresis. It uses the formulas we derived in the comprehensive comparator hysteresis design video. In that video, we derived some equations to calculate component values for the resistors. It implemented the reference voltage as an independent variable. It implemented the pull-up voltage as an independent variable. It implemented the low-level output voltage of the comparator as an independent variable. The principal concept was to make the hysteresis resistor have a significantly higher current than the input bias current to reduce errors caused by the input bias current. The formula for R2 was derived based on all those aforementioned values. The coefficient A was made since it appeared 4 times in the equation. Then the equation for R1 was derived using RH and R2 as inputs. The development of this spreadsheet encompasses several techniques covered in numerous previously posted videos. The LM117, LM317 voltage regulator calculator covered cell styles, cell names, sheet protection, and more. It also dynamically linked component value labels in the schematic to the associated calculated cell. The E-Series user-defined function developed Visual Basic for Applications code to return the closest standard component value from the various E-Series values. We also developed code to return the SI engineering prefix for a given value. It scaled the number accordingly and returned the number as a text with the associated SI prefix. Another spreadsheet was developed to select standard component values, the SI prefixes with units, including the D-rated next highest power rating of resistors. I also made a video about foolproofing engineering workbooks. Of course, as I mentioned in the video, there's no way to make a workbook entirely foolproof, but you can go a long way with using data validation for inputs and protecting the cells with calculations. I also made a video about digitizing specification plots. This is a method of converting a digitized plot in a spec into an equation. We will utilize that for the low-level output voltage of the comparator. The Sol and Key component selector video introduced a drop-down selector for the desired E-Series component values for the resistors and capacitors. The workbook for this video will utilize that as well. One new feature introduced here is the use of hyperlinks. I'm sure you are familiar with the primary use of a hyperlink to a web page. We will do that using a YouTube link to the associated video for this spreadsheet. But we will also make use of a link to a place in this document feature. When a workbook has several tabs for worksheets, it can become more confusing when a variable is displayed on a sheet that references a variable in another worksheet. In this case, a specific cell name reference for the low-level output voltage of the comparator. I don't need to make you watch me construct this workbook. I'm just going to go over the highlights and provide a link to the finished workbook in the details section of the video. Here is the workbook. Let's begin by looking at the Device Specs tab. I pasted a snip of the page that has the relevant specifications, in this case the LM339B. The input bias current at 50 nanoamps, and the typical output sink current, which is really the maximum you would want to use, in this case 21 milliamps. Next is the input logic device specs, the Lattice ISP Mach 4000V. The low and high level input currents are 1 microamp, and the Logic 1 minimum input voltage is 2 volts. I encourage you to watch the video on foolproofing engineering workbooks. I'll show the data validation details I used in this workbook. First input is the pull-up supply voltage. Select the Data tab, then Data Validation. You can also use Alt plus D, then L. The allow criteria is decimal, data is greater than, and the formula equal to VH. The input message has a title and a description of its property. The error alert style is stop, and with a title of out of range, and an error message that the input must be greater than VH. Now moving on to the reference voltage input. Its validation criteria are the same as the pull-up supply, requiring the input to be greater than VH. The input message again is a description of the input, and the error alert is similar to, stating that it must be greater than VH. VH, the high-level threshold voltage, is different. The custom allow criteria is an AND function where VH must be greater than VL and VH must be less than the reference voltage. The input message has an informative title and description. The error alert message says the input must be greater than VL and less than VR. For VL, the low threshold voltage, the custom allow criteria is an AND function where VL must be less than VH and VL must be greater than 0. The input message has an informative title and description. The error alert message says the input must be less than VH and greater than 0. The resistor series is a drop-down box referenced to this table, which has the E-series descriptions and their associated E-series function arguments. Going back to the drop-down, notice the data validation setting. I allowed the list to only span Q4 through Q8. Going back to the table, Q4 through Q8 is E12 through E192. I figured nobody would ever use a wider tolerance than 10%. The resistor series looks up the applicable argument for the selected cells, in this case 6 or E96. To compute a pull-up resistor value, an input called scale of output sink max is used. It's simply what percent of the maximum sink current you desire. It's formatted as a percentage. Let's look at the data validation for that cell. It's a custom type with the AND function again, saying that SF sink must be greater than 0 and less than or equal to 0. It has an informative input message and an error alert that says the input must be greater than 0 and less than or equal to 100%. The scaled output sink current is the output sink current max times the scale factor percentage. The low-level output voltage is calculated from the fourth-order polynomial from the digitized spec plot. This is the VOL versus the iSync spreadsheet. The low-level output current is copied from the main spreadsheet. The low-level output voltage is computed from this polynomial using the coefficients here. The resultant VOL on the comparator circuit spreadsheet will reference this cell. I also made a graph of the output voltage versus the output sinking current. It has an array of IOL values and the calculated VOL using the polynomial. A single marker in orange shows where the calculated VOL is on the curve. The pull-up resistor is calculated as the pull-up supply voltage VP minus VOL over IOL. That calculation is placed inside the E-series function, with the series argument being the R series from the resistor series lookup table. The high-level threshold voltage is calculated with this formula. The note for the cell is the high-level threshold voltage must be greater than the logic device V minimum. The load on the pull-up resistor in the open state is the sum of the logic device high input current and the comparator's output leakage current when open. Below the cell is a caution message that is displayed if the high-level threshold voltage is below the logic device's spec. I'll set the scale factor of the output sink current to a really low value to demonstrate it. Now for the hysteresis resistor calculation. The user input is the input bias scale factor, as described in the Stop Selecting Arbitrary Resistors for Hysteresis video. The scale factor is to ensure the current through the hysteresis resistor is significantly larger than the comparator's input bias current. The typical value is 100. Let's look at the data validation for this cell. The validation criteria is allowing a decimal number greater than 1. The input message has a meaningful title and message. The error alert has a message that the input must be greater than 1. Next is the minimum voltage across the hysteresis resistor. It uses the min function to return the smaller of VL or VP minus VH. The cell to the right displays text indicating the minimum VH. In this case is VL. The hysteresis resistor is calculated using this formula, which is placed inside the E-series function, with the series argument being R-series from the resistor series lookup table. Moving on, we will calculate the value of R2. First, the coefficient of A is calculated, then the big formula for R2. Notice how using cell names makes this formula much more readable. It also uses the E-series function like the others above. R1 is calculated using this equation, also returning a standard value resistor. In the comprehensive comparator hysteresis design video, we derived the formulas for the resultant thresholds using the standard resistor values. I also calculated the percentage error between the input thresholds and the resultant values. Since the calculation of R1 is based on the value of R2, which is a standard value to begin with, the error percentages come out very low. Let's introduce a new feature in this series, which is hyperlinks. I have the text video comprehensive comparator hysteresis design here. Notice I merged cells A2, B2, and C2. Let's make that a hyperlink to the YouTube webpage for that video. From the Insert tab, select Link. It will already have the text to display the same as what's in the cell. I'll paste the address link. Now it's a hyperlink. Let's go edit it. There's a screen tip function where you can put in text that will be displayed when you hover the mouse over it. I'll paste in the text and click OK. Now you can see the screen tip. Notice I'm hovering over the right side of the link. If I had not merged the cells that are within the extent of the link's displayed length, the screen tip would have only been displayed when hovering over cell A1 where the link is in. You can also make a link to a specific spot in the workbook. The VOL in C12 is referenced from the VOL versus SciSync worksheet. With the cell name _VOL calc. Now insert a link, and from the Link To set of buttons, select Place in this document. You can type in a cell reference on the current sheet, but we want it from another sheet. Scroll down to the Define Name section and find the cell name we were looking for, which in this case is _VOL calc. You can also give it a screen tip. I'll paste in some text. I think the screen tips are helpful for the user. If you think these tables are distracting to the user, you can hide them. Just select the columns, right-click, and select Hide. Finally, let's protect the sheet so the calculation cells are not overridden. You can use a password if you like. I hope you got something out of this video. Hopefully these can be some features you can build into your electrical engineering spreadsheets. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.